as we discussed last class, uh, we did a little bit of background on power systems first, in general power engineering, last Monday. Last Thursday, we did a quick basic recap of economics, and today we'll get started with optimization, which is going to be one of the key analytical foundations through which we are going to look at pricing. So I want to introduce optimization today. We'll spend more time just trying to understand the modeling aspects and some key concepts in optimization, certain more heavy things in terms of conditions for optimality and any related proofs or something are not the crux of this course. I'll try to give you intuition as much as possible, okay? But we'll try to bring in wherever necessary some quick proofs. If they can be introduced, we'll try to do it. But please note that this is not an optimization course. So you have to look at it from that perspective, okay? All right. So what we're going to focus on today is just two basic things. One, we'll do a quick introduction to optimization. Primarily, when we talk of introduction to optimization from the context of this course, what is optimization? How do you frame a certain decision-making problem as an optimization problem? That is what we'll focus on right now. And then we'll look at some examples of unconstrained optimization and certain key results that come in that class of optimization problems. That is the focus of today's lecture, okay? So, let's start with a quickie. How many of you think you optimize something or the other? What is optimization according to you? Anybody? Yeah. All right. So, keeping in mind certain trade-offs, you're trying to maximize a benefit. That's a type of optimization. Any other example you may want to give? Minimizing the for certain purpose, right? You have a certain purpose in mind, and to achieve that purpose, you want to minimize the resource you use for it. All right? Anything else? Very early on in the first class, somebody discussed optimal bidding, and we had a short discussion on optimal bidding. You guys recall what that was? Is there any optimization there? Optimal is a part of the name there, so obviously there must be some optimization going on when you're trying to optimally bid. What is it? So you may be incurring certain cost and you want to try and make a profit over that cost and yet try to get a contract or something, and that may be a part of how you frame your bidding strategy for trying to attain whatever it is that you are trying to attain by bidding for it, right? Okay. So you basically, these are all classic examples of optimization, examples that get written out in papers also. But we do optimization in day-to-day life also, right? You go to the market, you go to buy tomatoes, there's going to be one vendor who's selling at 120 rupees a kg and another vendor selling at 100 rupees a kg. For all intents and purposes, if the quality of tomato looks the same, then you'll go in for the 100. No, you'll not go in for 120. Okay, obviously you're not doing an exhaustive search. You're not looking at every vendor and saying, oh, your quality and your price point, your quality and your price point. But within the set of, some reasonable sort of alternatives, you would want to pick the best possible alternative for yourself. And when you're trying to make that choice for the best, inherently you're doing optimization, correct? You want to have a night out with friends. You want to enjoy dinner outside. Everybody will have constraints. Oh, I don't want to eat this, I want to eat Chinese, I want to eat Pan-Asian, and then, you have all these various constraints. And then, of course, budget is a bigger constraint than anything else, or at least it used to be when we made decisions. I don't know about Gen X or Gen Z or whatever it is that you guys are, but budget is still going to be something, right? It's going to drive something for you. And plus, and then, other sort of intangibles like brand, and then some sort of, there might be certain coupons they are offering, and you're going to try and get maximum benefit out of use of a particular discount for a group of something, or, whatever it is. Again, you're optimizing there also. It may not be a optimization problem you could write as, some f of x, minimize subject to constraints and so on, but you're still optimizing given the set of, variables at hand for you to play around. So optimization is something, of course, you do in day-to-day life, okay? When we are talking of optimization in the context of this course, there are several problems, like the bidding problem we discussed. Or you may have a particular demand to meet, and you want to make sure you use your most efficient resources to meet that demand. You're trying to optimize on efficiency. Efficiency could be simply efficiency of input output, efficiency of cost, whatever way you want to define that efficiency, correct? So optimization can take place at various different places in your life, and particularly in this course there are several things we are going to look at, particularly from pricing perspective, particularly when we are trying to figure out how to meet demand in the best possible way, where optimization is going to kick in. So what we discuss here today is going to serve as a foundation for several different problems we deal with later on in the class that will use the underpinnings of what are being discussed here, okay? Unconstrained optimization in particular is the simplest form of optimization, where you just have the objective that you want to either minimize or maximize, but there are no particular constraints, which is very unrealistic. I mean, real world problems will always have some sort of constraints, but we start with unconstrained optimization problem. It gives us a certain key insights, and then we build on to how typical optimization problems are constrained optimization, okay? All right. So what we do when we think of optimization from a mathematical perspective is you think of what is it that you want to maximize. Is it a cost you want to minimize? Is it a benefit you want to maximize? Is it a reward you want to maximize? Is it a penalty you want to minimize? Whatever may be the category, you want to frame that function or that objective as a function of the decisions you can take. And these could be multiple decisions. Here in particular, I'm saying there are n possible decisions I could take, and what I'm trying to optimize, the cost or the reward or the benefit or the penalty, I know that there is a mapping of these decision variables into this particular f, okay? Now, in particular, this f is, it's taking something in Rn to something in R. Okay, I am not talking of multi-objective optimization here. I have a set of decision variables and I know how they get mapped onto cost or reward or penalty or what was the other thing? Benefit, right? But at the same time, there are not multiple things I want to optimize. Multi-objective optimization. A classic case could be in this particular classroom, I may want to minimize energy consumption, but optimize comfort and maximize comfort. The decision variables for both are how I run my air conditioners, okay? X is a set of, set points for my air conditioners. But here I have two different Fs. I have a minimize energy wala F and I have a maximize comfort wala F. I'm not dealing with that category of problems at all. I'm dealing with single objective optimization. So F is going to be mapped onto some real number scale. All right? Makes sense? Okay. Now, so when I'm talking of optimization problems, I'm necessarily talking of what sort of choices I could make for x1, x2, all the way till xn, so that this particular f is either minimized or maximized. That is what I'm talking of when I'm talking of maximization problems. Okay. So we start off with the general case. In the general case, I may have, let's say I'm going with, I want to minimize f of x. X is again in Rn. All right. So this is not f of x, it's actually f of x1, x2, x3, xn, all the way like that. All right. So if it makes it easier, let's write it exactly like that. Okay. So x1, x2, xn. All right. Okay. I may have certain constraints. So I want to make sure, for example, that this is what we call as an equality constraint. Okay, I have a set of constraints. I take x1, x2, x3 and I have a function which maps this x1, x2, x3 as some function g which we want equal to 0. Okay? And then, there may not be just one such g, I could in fact have multiple such g's. So let's say I have capital I such equality constraints. Okay? All right? And then another set of constraints I may have is a set of inequality constraints. Okay? All right? Again, these are not one constraint, but j such constraints. All right? Okay? Everything makes sense? Now, any set of x1, x2, x3 that actually meets these constraints, okay, that is what I'm going to be calling as a feasible decision for me. All right? And any set of x1, x2, x3 that of course meets the constraints and also minimizes the objective function, that is my optimal decision, simply speaking, right? Let's put it in context. Let's look at an example that is close to this course. We have two generators. We want to decide how to run these generators at minimum cost, okay? And when I say how to run, I mean at what points to operate these generators at minimum cost so that a particular demand gets satisfied. Can you help me frame this problem? And then we can map it to this framework. Okay, so this is the general framework. Let's look at a particular example of this is what we call as the economic dispatch problem. And I'm simplifying the problem here, only two generators, a particular demand that they have to cater to. We want to find out how to run the generators at what operating points so that I can minimize the cost. So, how do you want to go about mathematically framing this? The problem in words is understood, but there has to be maths put behind it. So, what sort of functions would we need to start with? We of course need some sort of objective. So, what would be the objective here? The cost function itself. Now we have, so I want to spend a little bit of time here so that you get insights on the modeling as well, right? Because the theory of optimization is one part of it, but the modeling that goes into it is also going to inform what sort of outcomes you get out of it. So when we are talking of cost here, we have two generators. Do you think the cost of one generator is going to impact the cost of other generator? In other words, should I have a cost of x1, x2 where is the x1 is the output of first generator, x2 is the output of second generator? Is that what we are looking at? Is this the general structure we want, or is this a general structure we want? Second one is easier to solve. Second one is also, more likely sort of scenario, right? Because generators typically tend to be separated by technology and so on. And so, for example, how you run your coal generator, why should it affect the cost of running your gas turbine? The coupling between them, of course, exists because they're serving a common demand. But that coupling need not be captured in cost. The cost itself, given the costs are purely going to be dependent on what is the load on the generator individually, not together. But together, they have to serve a common demand. So I have to figure out how x1 and x2 interact with each other through these constraints, not necessarily through the cost. So this one may be a much easier way of looking at it. There might be cases where you may have to adopt something like this, because the startup of one generator may affect the startup of another generator and so on. But for the intent and purpose of this particular example, since I'm simply trying to figure out how, what is the operating point of the generator. I am not necessarily looking at startup and so on and so forth. I think this may be an okay sort of assumption to make, that the costs are only dependent on their own operating points, and you could go ahead with this as a way to solve your problem, correct? So your objective is going to be this. This is what you want to minimize. And what are the decisions available to you? X1 and X2. This is what your deciding factors are. But this is still one part of it. And we've only looked at this particular objective has been framed. What else would be the parameters of the problem? The demand has to be satisfied. And since we are talking of a particular value per se, so we may have, for example, X1 plus X2 being equal to meet some demand. This is an equality constraint. There's a perfect equal to here, right? It's not just about equal to demand. It's not more than demand. It's not less than demand. It is exactly equal to demand is what I have framed here, which makes it an equality constraint. It would fall under this category as soon as I wrote X1 plus X2 minus D equal to 0. That is how I would translate it to G of X1, X2 equal to 0 category. Makes sense? Yeah? How many equality constraints would this problem have? This is one. Do you see the need for any other constraint in an equality constraint form? Do you see the need for any other constraint? What sort of? Some amount, right? There are some capacity limits, right? So this is the classic demand constraint. I have to meet the demand. And then I would have capacity limits. So I want X1 to be within particular limits, right? So X1 some maximum, X1 between some minimum, correct? And in fact, this would be, I could even write it as I. This would hold for both generators where I is equal to 1 and 2. All right? Make sense? So in total, how many inequality constraints do I actually have in this problem? 4. 2 upper limits, 2 lower limits, correct? So my problem has one equality constraint, which is making sure that whatever choices I make meet my demand. And then I have 4 inequality constraints that are ensuring that whatever is the outcome of this optimization problem is something that the generators can physically produce. I'm not violating any capacity limits on the generators. All right? These capacity limits, in fact, the maximum limit is something that is well understood. Where does the maximum limit come from? It's just the rated capacity of the generator, right? It's not, it can't just produce infinity. It is going to be at some rated capacity. So the maximum limit is understood. Where is the minimum limit coming from? You're eventually framing a math problem and you're trying to minimize cost. It should not ask you to produce minus 100. So 0 is an obvious minimum limit, but certain generators may even have a other technical minimum outside of 0. It may need a certain minimum load to guarantee economic feasibility. Beyond, say for example, a 500 megawatt generator, beyond 100 megawatts, it's actually, very, very energy inefficient. The amount of fuel you burn for the amount of output you get, it's at such poor energy efficiency that range is not an economically viable range between 0 to 100. And so there might be a technical minimum on it, nothing below 100. Okay. There could be other reasons where the generator may be physically incapable of producing anything below 100 megawatts. All right. So all of this, economic minimum, technical minimum, together we may decide what this X1 min is going to be. So there are a class of generators, especially your big plants, for which these sort of limits would exist. Your nuclear plants, for example, they have a complete supply chain mechanism worked out to ensure that they can burn the right amount of, not burn, I mean, they can, use the right amount of uranium and so on. And so beyond a particular minimum, they will not operate. They want that much load on their system for sure. Likewise, there might be economic minimums in terms of energy efficiency for your coal generators. The gas turbines, on the other hand, diesel generators, they could run at 0 or they could run at their maximum, and they're usually small in range also. So they're a lot more flexible. So there you could have a 0 and say a 50 or 100 megawatt capacity as limits as well. Okay? Makes sense? Everybody okay with this? You could take care of efficiency in the cost as well if you have a sort of formula for it. But then what happens is, unless it is implicitly leading to some sort of dollar values that you have, you may end up with a multi-objective optimization, which is a class of problem, again, I'm not dealing with, right? And in efficiency, you may not necessarily want it to be at the maximum possible efficiency, you just want it to be within a range per se. So it makes more sense to just have a constraint rather than, yeah. The maximum possible efficiency typically happens at a very small range, and that would limit how much you can extract from the generator. Like for the diesel generators, I drove a curve last time. If I don't remember, did I draw it in the class? Yeah. So that's usually a very small range where it's going to get your best possible efficiency. So if you were only operating your generators at your most energy efficiency point of view, that point, then there's only a certain categories of demand you can serve, and anything in between you may not be able to serve at all. So you don't think of energy efficiency from that perspective. You just make sure that it is at least somewhat in an efficiency range and you leave it at that. Yeah. It's a very demand driven system. You want to make sure you meet the demand in the lowest cost possible, but you want to also make sure energy efficiency doesn't just go for a toss. So you want to have certain minimums and maximums, but yeah, not exactly always trying to maximize efficiency. Okay? Makes sense? Everybody okay with this? And the link to this is clear. Can we visualize this? Okay? If we have to visualize, how would this look? What are the dimensions in which we are optimizing? We have 2 dimensions, right? So we have x1 and x2. Just for the sake of it, x1, x2, you could flip it around, doesn't really matter. Let's start with the feasible region. What would this look like for us? If you were only looking at this, for sure, but then there is a line, right? Correct? So again, let's put some numbers. So that let this be, say, for the first one maybe 20 and 200, and then for the next one 0 to 100, let's say. Okay, so 20 and 200, all right. And then I said 0 to 100, right? So 0 to 100. And this may not be to scale on either side. Am I on scale? Yeah, maybe. Yeah. So this is clearly it's somewhere here, but I still have to have x1 plus x2 equal to something. And let me give you a value for demand. Let's say the demand on this system is 150, right? So I take, this is 100 somewhere here, so 150 and then 150 here, and so something like this. Any x1, x2 that lies on this line is going to be within the limits of generation, correct? And it is making sure that x1 plus x2 is in fact equal to 150, correct? Now, what is this line? What is this line? This is my feasible region. Any x1, x2 that satisfies the constraints. So any x1, x2 that I pick on this line would satisfy the constraints because it is going to be within the limits, right? And it is going to meet the demand, correct? And so any x1, x2 here is feasible for me and good enough. but I want to go beyond feasible. I'm looking at optimal. So I want to have an x1, x2 here that in fact also optimizes the cost. So how do I pick that? What do I do now? I'm still looking at only this part. I've not yet brought in the cost. Correct? I have to now start looking at what would be, how would f of x1, x2, in this case this c1x plus c2x, how would that look and how would that intersect and interact with this feasible region? And when I look at that, that is when I'll start looking at optimality. What we have here is just a way to visualize your feasible region. When you have to now look at optimality, you have to think of translating this onto this region. And what's the best way to do that? We'll look at it in a bit more depth later on, but what do you think would be the best way to do that? You have to look at the contour plots for the f of x1, x2 and start projecting them onto your feasible region and then look at where you would in fact get to the minimum. The intuition for this we'll start building, but the best place to start is unconstrained minimization, and from there we move on to in fact what happens in the case of constrained minimization. Okay? All right? All good? Any questions so far? Any questions on this? Okay? So, forget the constraints. Let's just look at what happens at when you try to minimize something. That particular function I have drawn there, okay, we have a single objective function and only a scalar optimization. When I say scalar optimization, I don't have a x1, x2, x3. I only have a single decision I have to take. Okay, I'm starting with scalar optimization simply because it makes it easier to visualize certain results. N dimensions becomes hard to visualize and particularly hard to even, plot and something. So it's just easier to visualize. And I'm looking at a minimization problem. Okay, this is my f of x and this is where I'm plotting my x. And visually, very quickly, this is the point of interest to you. This is your minima. This is your minimizer, correct? This is the point of interest for me, correct? All right. Now, at this point, if you look at this, you move away from this point in either direction, the function value is increasing. This is your classic property of a minimizer, correct? So, when you define a minima, around the neighborhood of that minima, you should see the function increasing, which is what makes it a minimizer. The reverse would be true for a maximizer. If you were at a maxima, you should see the function value drop as you are in the neighborhood. Okay? Does that make sense? Okay? The same function, if I was to just take a mirror image of it, instead of looking at f of x now, if I was looking at minus f of x, correct? Then that same function, the same point x star would in fact end up maximizing minus f of x. Okay? This makes sense, right? And which is why we don't have to think about, oh, are you trying to minimize or are you trying to maximize? If you're trying to minimize f of x, it is the same as maximizing minus f of x. One and the same thing, or vice versa. Correct? You don't need to bother about this. And this works in n dimensions also. It's not just for scalar optimization. This works in general. Okay? All right. Now, what do you see here? Here, you can see that this particular function is not as nicely defined as the earlier one. It is more classic of all the possible ways your f may be defined, right? It has convexity in certain regions, it has concavity in certain regions, which means you may have for the same function along that range of x, minima, maxima, and inflection points, correct? And that is what you see here. x1 and x4 are both maximas. If you can establish a neighborhood around which they will have the maximum value, correct? Whereas if you look at x2, it's a minima. Okay, sorry, that line has gone off a bit, yeah, but around x2 you can see a minima, correct? Whereas x3 is where the function changes in its convexity. So that's your inflection point, correct? One thing that all of these points have in common is what? What is happening at these points? And there's a clue embedded in the file image. Yeah. Slope, correct? At each of these points, the gradient is in fact 0. And this is your first condition to know whether you have arrived at a minima or a maxima. And this makes sense, correct? If you go back here, or if you were looking at it here, the function, as you approach x star from this side, the function is dropping in value. As you move away from x star on this side, the function is increasing, which means the slope, of course, has to change signs as it passes through the minima. So at some point, you have to have f of x star equal, gradient of f of x star equal to 0. And that is in fact your minima. Make sense? Correct? And this is true for a maxima as well, but it is also true for a saddle point, okay? All right, or at the inflection point, also true. So it's not enough for us to know whether gradient of f is equal to 0. To be able to categorize at whether you have arrived at a minima or a maxima, something else would be needed. And what is that something else? Sorry? Double derivative. Because if you were at the minima, your function value is dropping, arrives at a minimum value, and then it increases, correct? So what's happening to your gradient? It starts off being negative, negative, less negative, then 0, and then it is going to increase, correct? Right? Whereas if you were at a maxima, if you look at that function now, right? Your function value, as you approach the minimum, say from the left hand side, is going to increase, 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 go to 0, and then decrease, 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 correct? Which means your gradient, it's always decreasing. Makes sense? Yeah? So you don't just look at the gradient of f, you in fact look at what's happening to the double derivative, and based on that, you categorize whether you've come at a minimum or you've come at a maximum. Make sense? All right. Any questions so far? Okay. So if we were to formalize it, I'm just first formalizing, I'll go back to the remarks. Okay. So the necessary condition, if you're not at a point where your derivative is 0, where your gradient is 0, you can safely say you're not at a minimum. It's a necessary condition, correct? So necessary condition means you can of course use it to say when you're not at the solution, correct? The sufficient condition, so the clinching deal is you know whether your gradient is 0, and then you check for your double derivative. If your double derivative is positive, more than 0, then you know that you have arrived at a minimum. If you were looking for a maxima, you have to look at double derivative less than 0. Okay? Make sense? Everybody, so far so good? Yeah? Alright. Now, very quickly, it could happen you are dealing with real world optimization problems. You will essentially code it. You'll use Python, you'll use MATLAB, you'll use something. In your coding, you may end up making mistakes. You may end up coding for something which makes your problem infeasible. Okay? So, I gave you some examples here, right? What if the demand I had to cater to on this system was 350 megawatts? Could I deliver a demand of 350 megawatts on this system? No. Even if I was to run both generators at their maximum, I can never meet a demand of 350 megawatts. The maximum capacity of one generator is 100. The maximum capacity of another generator is 200. What does that make my problem? Infeasible, right? Okay, and you need to, if you have an infeasibility in your constraints, then that means basically you can't go ahead and optimize anything on it. And that you need to be very, very careful in terms of how you're framing your problem. Infeasibility may come because you've not really posed the problem well. Infeasibility may come because you didn't code the problem well. Both are sources of infeasibility, okay? So make sure that you frame your problem well and make sure that you translate it well into a syntax. What happens if your function is unbounded? Then you could essentially just go on minimizing, and you could attain minimization at minus infinity, which makes no sense. There's no bound on it. It's not countable, correct? So these are things that you have to worry about. More generally though, if you have functions, your f, your g's and your h's, if they are continuous and the feasible region, what we drew here, or more generally the shape it would take in terms of how the g's and the h's interact, if that is bounded, okay, then essentially Weierstrass's theorem, very early on he established that there will be a solution, okay, and so you could have a optimization problem solved there. So when you have, for example, these sort of limits, and your there is some sort of continuity in your cost functions, essentially you're dealing with a class of problems that have a solution, and you can always then find a solution. Make sense? Okay? For most problems in this class, we would in fact have some sort of nature of problems which would ensure that you know there is going to be a solution. You just have to find it. Okay? The conditions were still holding. I mean, but the problem is that there is infeasibility in terms of just the limits. You no longer there. It's not the theorem doesn't in fact invalidate itself. It's just that the feasible region is not defined for it anymore, right? There is no feasible region. So that you can't even say whether it's bounded or not. It doesn't exist. That's the problem. Yeah? Make sense? Any questions? Any other questions from the audience? All right. Okay. When we talk of the conditions here, we were still dealing with scalar optimization. When you go in n dimensions, the same optimality conditions translate to conditions on gradient and translate to conditions on the Hessian. Okay. So, if you have a f of x, or as a function of x1, x2, x3, xn, correct, you want to make sure that you are at a minimum when the gradient of f is equal to 0 and the Hessian, okay, it has to be a positive definite matrix. What does this mean? Do you guys recall what this means? This is easy to see. You would just have to take the partial derivative of f with respect to x1, x2, x3, set that to 0, and that's going to give you a set of equations relating x1 and x2. What about this? What is this? This is going to be again a matrix, right? You're going to have a D and on this side same thing. A whole matrix like this, correct? And then this matrix, what do we want this to be? We want this to be positive definite, which means what about the eigenvalues of this matrix? They should all be positive, correct? Okay, all right, makes sense? Yeah. Can we do one quick example? That's the function. You have to, the solution is already mentioned there, okay? You get those points essentially by solving your gradient of f equal to 0 conditions. Maybe we can solve it together. So f of x is x1 cube plus x2 cube plus x1 square plus 4x2 square plus 6. So when you do gradient of f, what do you get? What's the first one? Then you have correct? Which one? I'm sorry. Where am I? Yeah, sorry. True. Thank you. Yeah, sorry. I took care of it here. I forgot to take care of it here. Thank you. Yeah. So what are the possible points? We want to set this to 0 and then you're going to get a possible set of x1s and x2s. So what are your, you set this equal to 0. What do you get? What possible combinations of x1, x2 do you have? Clearly 0, 0 is one point. Yeah. What else? You're going to get yeah, 0 and then minus 8 by 3 because from here, and then 0 here and minus 4 by 3, correct? And minus 4 by 3 and minus 8 by 3, correct? All of these are stationary points. This is where your gradient of f is in fact equal to 0. But now you want to figure out which one of them is the minima, which one of them is the maxima. What do you do next? You look at the Hessian of this. This is a clean Hessian. You just have diagonal terms on it. So they would purely be dependent on x1, x2 in fact, right? So if you look at the Hessian, what would that be? Easiest part is done. So you have 2x1 plus 4 and what else? 6x2 plus 8. Yeah? Makes sense? And because it's a diagonal matrix, eigenvalues are going to be that much easier for you guys, right? So you plug in x1, x2 now, and you should be able to, all these x1, x2, when you plug in, look at the eigenvalues and you should be able to see, what did I make a mistake? Yeah, sorry. I'm so sorry. 6x1. 6x1 plus 4. So x1, when you put 0, you have 4 and 8, correct? What does that make this? Is this a positive definite matrix? Yes? Yes? Correct? And that makes 0, 0 as your minima, correct? If you put 0 and minus 8 by 3. So when you put minus 8 by 3, I think this is going to be, so minus 48 and 3, 16, minus 8. So you're going to have one positive eigenvalue, one negative eigenvalue, which means it's neither positive definite or nor negative definite, which makes that a saddle point. Okay? All right? What else? The next one, minus 4 by 3 and 0. So this is 0 and this would end up being a minus 4 by 3. So minus 4. Again, you have one positive eigenvalue, one negative eigenvalue, making that also a saddle point. And when you plug in minus 4 by 3 and minus 8 by 3, you will have two negative values here. So negative definite matrix, negative eigenvalues, and that makes that particular point a maxima. Okay. Just to try out, take this function, plot it in your, you have all this plot functions available in Python. Very quickly you could plot it and you should be able to see this in 3D and you should see how the saddle points look and you should see how the minima and maxima looks. Okay. Now I don't have it for this particular function, I think, but the saddle point actually looks something like this. The extreme right plot is showing you a saddle point. What happens at a saddle point is the function is getting maximized for one particular, either along x1 or x2, and it is getting minimized along one particular the other dimension. So it's a classic min-max point, and in fact, it has some very important sort of connotations in game theory. You know, for certain category of games, you may in fact be looking for saddle points because they meet certain criteria, min-max criteria. Okay, so but in optimization, it means nothing for us because we want to be either at a minima or a maxima. So when you're dealing squarely with minimization or maximization problems, we are interested in locations where your gradient is equal to 0 and your Hessian is either positive definite or negative definite. Make sense? Everybody okay with this? Yeah? All right. So let's do a very quick recap. We have 5 minutes and then I'll stop. When we are dealing with optimization in the context of this course, we are going to be dealing with single objective optimization, never multiple objectives. Many categories of problems, in fact, end up being multi-objective optimization. You want to get the best possible comfort at lowest possible energy. You may be familiar with this problem, Aryan, right? You may want to get the best possible rewards, but you want to spend the least possible cost for it or something. Again, many examples of multi-objective optimization problems, but that essentially implies that you need to translate your decision variables, x1, x2, x3, how many ever decisions you have, into 2, 3, as many objectives as you have. And it requires a visualization of these objective functions and how they interact together so that the trade-offs are clear. We are not going to be dealing with that category of optimization. We'll only be looking at single objectives. And there's a wealth of problems within those objectives. For us, we may be interested in minimizing cost. When we talk in terms of the markets, we may be interested in maximizing surplus for a producer. We may be interested in maximizing the social welfare for the system. We talk of efficient allocation. We talked of the welfare theorems last class, right? These are all problems where we could take the set of decision variables for us and then map it onto that particular objective of interest to us: cost, social welfare, producer surplus, consumer surplus. These are the category of problems we will be dealing with in this particular class. So, we will be dealing with single objective optimization. More importantly, constraints and how they interact with the objective function. This is something that is going to be of very much of critical importance in this course. We started with unconstrained optimization simply because it helps us visualize certain important properties, like gradient being equal to 0 when you are at a minima or a maxima is an important result. It helps you understand how algorithms may be built to in fact find a minima or a maxima, correct? But that's only so far as it goes. Real world problems are more often than not full of constraints. So much so that you have to worry whether you even have feasibility in your problem at all. Okay, so we are going to focus on constrained optimization. Next class, we'll start with certain results that hold in the category of constrained optimization. All right, so we'll start there, and this is where we'll stop for today. If you have any questions, this is a good place to ask any questions. Thank you.